Hi everyone, welcome to my YouTube channel Study with Soumya. I hope you all are absolutely fine. First of all, if you are new to this channel or if you haven't subscribed the channel till now, make sure to subscribe. It will be helpful for you and it will motivate me as well to make such beneficial and important videos for you too. So make sure to subscribe. Also, when subscribing the channel, don't forget to turn on the bell icon so that you don't miss any important update or opportunity from the channel itself. Also, make sure to be a part of our Telegram channel. The link for the Telegram channel is given in the description itself. Right, on our Telegram channel, we have lots of curious students like you for doubt discussion and all sort of things. So make sure to be a part. Well, in this video, we are going to discuss one of the most important sorting algorithms, that is quick sort algorithm. Now, this algorithm is very much asked during the interviews, and also it is very important algorithm. So I will try my best to explain each and every bit of that algorithm. But before this, let's understand some theory related with the quick sort. Well, as you know that in merge sort, if you are aware of this, so you will be knowing that merge sort, what is the heart? What is the base thing related to merge sort? That is merging. Okay. And here, what is the heart of quick sort algorithm? That is partition. You will be understanding this, that what is basically partition, what is the motto. We start this algorithm by taking a pivot element. Now, what is this pivot element? Randomly, you can choose any element as the pivot element. It's up to you. And here the strategy is that we'll be choosing any array element randomly as a pivot element. And then you have to make sure that all the elements to the left side of the pivot element are less than or equal to the pivot element, and all the elements to the right side of the pivot element are greater than that of pivot element, right? So this will be your pivot element, and the element in the left side will be less than or equal to that of pivot, and an element in the right side will be greater than that of pivot. So this is the first thing that we have to achieve here. Now you can see, it means if we are achieving, so if we are doing so, it means what? That pivot is on its correct position, or you can say pivot is on its sorted position where it should be. Okay, we are not sure about the left part, we are not sure about the right part, but pivot is sorted. This is what we can do. So this is the thing that we are going to follow in this quick sort algorithm, and this is how it will work. Okay, if you didn't understand anything, no worries, just stay connected to this video. Make sure to watch the video till the end, and I'm 100% sure you will be able to understand. Okay, so for example, let's choose a pivot element. I'm taking 7 as the pivot element, right? So this is the algorithm that we are going to follow for the partition, right? So now what we'll be doing, so I'll be taking two variables I and j, and initially both are pointing to, we are having two pointers I and j, and initially both are pointing to 9 itself. Now what is the use? So this j will keep track of that thing, that if any element during traversing, when we are traversing this array, that if any element occurs which is less than or equal to that of pivot element. What is our pivot element? That is 7. So what we will make sure? We will make sure to swap the value of I and j. This is what j is going to do. So let's understand further. Okay, so as of now, both are pointing to 9. Now 9 is less than or equal to 7? No, nothing will happen. Now we'll be incrementing the value of j. Now j is pointing to 6. 6 is less than or equal to 7? Yes, it is. It is less than that of 7. So what you will be doing? You will be swapping the value of 9 and 6. So now our resulting array is going to be 6, 9, 5, 0, 8, 2, 4, 7. Also, we have to increment the value of I after swapping. So now I is pointing to 9. Okay, loop will move further, and now j will be pointing to what? J will be pointing to 5. So this is where our j is now. Okay, again we will be comparing 5 to 7. So 5 is less than equal to 7? Yes, again the condition is true. So again what you have to do, you have to swap the value of I and j. So let's do this. So now what we are going to get? 6, 5, 9, 0, 8, 2, 4, 7, right? And after swapping, I told you have to increment the value of I, right? So now I will be pointing to what? This 9. Okay, because initially it was at this index, so now I value has been incremented, so it will be pointing to that index, right? I hope this part is clear. Now what we are doing, so again we will continue in the loop, and j value will be incremented and it will be pointing to 0 now. Again you have to compare, so 0 is less than or equal to 7, obviously it is, so again we have to do the swapping thing. So we'll be doing 6 5 0 9 8 2 4 7. So now I will be pointing to this 9, and again we'll be moving further, so j will be pointing to 8 now. Now 8 is less than equal to a 7, no, so we will continue in the loop, and now j will be pointing to 2. Fine. Now we'll be comparing 2 and 7. So 2 is obviously less than or equal to 7. The condition is true. So we have to swap the value of I and j. So now we are going to have 6 5 0. Here it will be 2, and here it will be 9 4 7. So now I will be pointing to 8 and j will be pointing to 9. Okay. Sorry. J will be pointing to what? J will be pointing to 4 now. Again we'll be comparing 4 and 7. So 4 less than equal to 7, yes, so again you have to swap the value of I and j. We are going to have 6 5 0 2. So here 4 will come, then here 8 will come, and here 7 will come. Now I value is going to be pointing to that value, that is 9, and j will be moving further, and that will reach to 7. Okay, and as soon as j will reach up to here, we'll be coming out of this loop, because you can say that now the array has been ended, right? So now you can see on which index this I is pointing to, on which index it is present. Don't you think that this should be the right position of 7? If I'm placing 7 here, then you will be able to see that all the elements to the left of the 7 will be the less than or equal to element of the 7, and right side element will be what? Greater than that of 7. So what we'll be doing after making these sort of iteration, at the end we'll be swapping the value of I and this pivot element. So we'll be doing 6 5 0 2 4, and here 7 will come, and here 9 will go. So this is our pivot element on its right position. So this was the sorted position where it should be. Now you can see all the elements to its left are less than or equal to 7, and to its right are greater than that of 7. So we have achieved our task. Now we have to do the same thing for this sub array or this partition. So you can see now we have got a partition, this partition to the left of 7, and this partition to the right of 7. Now we have to do the same thing for this partition and for this partition. So this is going to be a resultant array after placing the 7 at its correct position, right? Now this is the partition that we have to deal with, and this is the partition that we have to deal with. Now again we are going to follow the same approach for this partition and for this partition. Now again here also I am considering this 4 as the pivot element. So what is going to happen? So now again here we are going to have I value and j. Okay, so I and j are pointing to the initial element as of now, and here also I'm considering this 4 as the pivot element, right? As if you know that I'm taking the rightmost element as the pivot element, and now this is the array I have to deal with. Okay, this is the partition which I'm considering right now. So here you can see what, that 6, is it less than or equal to 4? No, right? So I'm going to increment the value of j. Now j will be pointing to 5. Again, 5 less than or equal to 4? No, right? So again I'm going to increment the value of j, and j will be pointing to 0 now. 0 less than or equal to 4? Yes, that is true. So what I'm going to do, I'm going to swap the value of j and I. Let's do this. So I'll be having 0 5 6 2 4, and you know that after swapping I have to increment the value of I as well. So I will be pointing to 5 now, and now again the j value will be incremented, and that will be 2. 2 less than or equal to 4? Yes, again the condition is true, so I'm going to swap the value of I and j. So that is going to be 0 2 6 5 4, right? And after swapping I have to increment the value of I, so I will be pointing to 6 now, and j will be pointing to what? J will be pointing to 4 now. So again I have reached to the end. I have reached to the pivot element itself. So our condition, the for loop condition that we are going to use, like is here, that is going to be false. So this is going to be my sequence. Now here you can see what, that the index to which I is pointing to currently, that is the right position for our pivot element, right? So what we'll be doing, we'll be swapping the ith position and this pivot element. So we'll be having 0, 2, 4, 5, 6. So again we have put our pivot elements to its right position. Now we have this partition and this partition, so we have to implement sorting for this partition and this partition, right? So let's see now what will happen. So again 2 will be the pivot element here, right? What I am going to do, I will be pointing, I and j both will be pointing to 0 itself. Now 0 less than or equal to 2, yes, that condition is true. What is going to happen, I will be swapped to the j value, but you know that I and j both are pointing to the same value, so nothing will happen, it will remain as it is. Okay, and now as if I have done the swapping, so I value is going to be incremented, that is going to be I, and again j value is also going to be the incremented. Okay, so as if I have reached to the last element of this partition, last element of this array, that is 0, 2. Okay, so again I will come out of the loop. Now at the last, what we are doing, we are simply swapping the value of ith element and the pivot element. Now again this nothing will happen here, because in that pivot element is at its correct position, right? 2 should be placed here. Okay, now what I'll be having, I'll be having this single element here, I'll be having this single element to its left side, so it will be remaining as it is, and to its right side I have nothing. So this part has been sorted. Again we are going to same thing here as well, so again as if this is already sorted, so 0, 2, 4, 5, 6, that is what I'm going to get from here. And now I have to do the same thing, same partition thing for this particular partition that is still remaining. So at the last I'll be getting what, 0, 2, 4, 5, 6, 7, 8, 9 as the sorted array. So this is what I am supposed to, right? So now you must have understood that how we are using this partition. So that's why I call this what, this is the heart of quicksort algorithm, right? So that's why we are using this partition strategy to place our pivot elements to its correct position. And we are now, let me show you that what basically we have to write in the quicksort, because you know that first we are considering this whole array and we are placing our pivot elements to its correct position. Then we are taking these partitions, right? We are taking these partitions, then we are again taking a pivot element and placing this at its correct position, and we are keep on repeating this thing. So let's see what logic we are actually writing to the quicksort algorithm part. So let me give you a hint, recursion will be involved here. So this is going to be a quicksort algorithm. Now you know that initially we'll be considering the complete array, right? Starting from the 0th index up to the last element, up to the last index, right? So here will be, to our quicksort function will be passing our array, then this p is going to be 0 and this r is going to be the last index of our array. Okay, now you can see that we were repeating the same thing, the partition thing, again and again for the small chunks that we were getting after placing our pivot elements to its correct position, right? So that's why we are using what, we are using recursion here. Now as we are using recursion here, so there must be some condition implemented, there must be some base case, so we have to put some base condition here as well, so that we do not go into the recursion infinitely, right? So that's why we are having this, that we have to do this calling and all, we have to call this partition quicksort and all till the time p value is less than that of r, right? Because when you can see when there was only one element like a 0 when we were discussing, so in that case we don't have to do this calling and all, so that's why we have put this base condition here, right? So you can see, first of all, we are using the complete array for putting a pivot element at its correct position. So by which we put 7 to its correct position, right? Now, you know that 7 has been placed at this index. So this partition function will be returning us that particular index where we have placed 7. Okay, so that by using that particular index, we can do the partitions, right? So what is the index where 7 has been placed? 0, 1, 2, 3, 4, 5, right? So now we'll be calling this quicksort function again on these partitions. So you can see we are doing the same thing here. A, p value will be 0, q minus 1, because we don't have to include that one. It is already on its correct position. We have to take from 0 to 4. That is 5 minus 1. And we want to do the sorting thing. We want to do the quick sort on the right partition as well. So we are doing here A, q plus 1. So q value is what? 5. So here, from here we want, right? So that's why 6 to r. R value is what? That is 7 itself. So now you must have understood that how quicksort is basically working. And even if you are facing any doubt, any problem, you can just comment. I will definitely try to reply. Now, just understand one thing. If I'll be asking you that, okay, just tell me one thing, whether it is a in-place algorithm or not, or why it is known as quicksort. Why such a name has been given to it, quicksort. So understand this. Well, I won't say that it's very efficient, and in the next video I'll be analyzing quicksort as well so that you can get a proper understanding. But it will work good in case of a smaller input, and it will work good than merge sort. Yes, you heard it right. Because in case of merge sort, we are taking an extra space. And here in case of quick sort, you can see we haven't taken any extra space. Whatever we are doing, swapping thing and all, whatever we are doing in the existing array itself. We are not taking any extra space. So here in case of quick sort, what is the space complexities? That is big of 1 itself, right? So that's why we can say it is an in-place algorithm. What do you mean by in-place algorithm? In-place algorithms are those algorithms which are not taking any extra space for sorting things. So you can see that quicksort is not taking any extra space. Now I'm asking you, stable, is it a stable algorithm? So we cannot consider it as a stable algorithm, because a stable algorithm is what? A stable algorithm is that when the equal values, for example, you are having an array 6, 5, 0, 4, 5. So let's suppose this is the array we are having. So here you can see this is 5, this is 5. So they are equal value. They are equal values. So a sorting algorithm will be considered as a stable sorting algorithm if the equal values retain their order even after sorting. Before and after sorting, the order should be retained. But here in case of quicksort, that is not fixed. It basically depends on the pivot element that you are choosing. So you can choose randomly any pivot element. You can choose 6 also, you can choose 2 also. But the thing that you should have to take care of, or the base condition, is that the element you have to arrange element to the left of the left of the pivot element in such a manner that they should be less than or equal to pivot, and to the right of the pivot in such a manner that they should be greater than that of pivot. So this is the algorithm that we are going to use. Now you can see this algorithm is directly doing what that we just discussed. So here you can see we are taking p and r. Initially p will be 0 and r will be what? Size minus 1. So size of this algorithm is what? 8. So 8 minus 1, that will be 7. So we are initializing the I value as p. Okay, that is 0, right? Because initially both I and p will be pointing, I and j will be pointing to the starting element. We have already discussed this, right? So now you can see j value also we are initializing with p, and you know that as soon as we will move to the last element, we have to stop right there. So that's why we are doing j less than r and plus plus j or j plus plus, you can write anything. Well, here you can see we are comparing if jth value is less than that of the rth value, a of r, it means the last element I am taking, because I have considered the last element as the pivot element. So that's why I am considering, I am comparing the jth value with the last element, because last element is what? Last element is my pivot element. So if this condition is true, then only I have to swap the value of I and j, a of I and a of j. Also, when I'm swapping, I have to increment the value of I as well. Okay, so this is the approach that we discussed. So it will continue like this till the time this for loop condition is true. And after coming out of the loop, I told now that I is pointing to the position which is the correct position where pivot should be. So that's why we are, after coming out of this for loop, we are swapping the value of I and r, right? So this is what we are doing. Okay, so this was the complete quicksort algorithm. I hope you must have understood this, and try to run this algorithm, try to dry run this algorithm by using certain array example and see how this is working. I hope this video has helped you to understand the flow of the quicksort algorithm, and you must have understood that how basically the algorithm is working. In the next video, we'll be doing the analysis of quicksort. Now let me tell you the time complexity. If you're talking about the average time complexity and the best time complexity of quicksort, so that is big O of N log n. And where's the worst time complexity is what? Worst time complexity is big O of n square. So in my next video, I'll be discussing that how it is big O of n log n, that is the average of best time complexity, and how in the worst case we have big O of n square, right? So make sure to subscribe this channel if you haven't subscribed this channel till now, so that you are not missing any important update or any important video. So subscribe the channel, be a part of our Telegram channel as well. I hope you have liked this video. So make sure to hit a like button and also give me your feedback regarding this video. Thank you for watching this video. Bye bye.